Everybody, hope you guys are doing well. So continuing on our journey, we were talking about concurrency, right? And then we came across synchronization, right? Why did we need synchronization, right? And we studied two measures for synchronization, right? So we studied the Coffman's condition. What do we want to achieve? And then we studied the Peters solution, and then there is bakery solution, right? So there is Peters solution, and then there is what do you say? There's one more. So Peter's solution is only for two processors, right? More than two processors, then we will run into an issue, right? So the other there was one more solution uh, that we were trying to understand, right? So before we go ahead, let's let's see. So let's do a recap. We were with we were studying with synchronization, right? That means what if there are so let's refresh a bit. Uh, what happened? Why isn't this working? Is okay. Let's get rid of this. So basically, first thing that we have is so this. Okay, here basically we have an application, right? Now this application can be any application, right? For example, say for example, I don't know what has happened. For example, this can be uh, so this is our weather app, right? So we have a weather application. This will be in the form of .exe, right? This will be exe file. So what will happen is so once we double click on this, so then uh, what happens is the code gets uh, moved into something called as RAM, right? So then we have made a double click. So once the double click is done, then our then the code goes in the RAM, right? So then the processes is created. So once a process is created, what happens is so each process gets its unique process block, right? Now what this block contains? First is it has a it is given a unique process ID. Then it has its own memory. So what are the two distinctive memory that we have? We have here a stack, and then the other one that we have is basically heap, right? So we will study about the stack and heap later on. So what does so now we have created the process, right? uh, okay, I'm using this board for the first time though, so is this the arrow? No, I'll show it. So the next thing that we have here is oh, there's a bar that comes. Okay, so what we said is we have the CPU here. So this is the CPU, right? And then we have this is the RAM, right? So what's the job of the RAM? uh, so here is what we have, the random access memory, right? So right now what we are going to do, so this is the processor. Just let's write this is So this is our processor. Okay, this is our processor, and then this is our random access memory, right? RAM. And then what happens is, once you double click on it, uh, that program gets a process block inside the RAM, right? So you'll be having, we have multiple uh, process block inside the RAM. So we have, this is right. The thing is, it has to join. I don't know why it's not working. I guess I need to hold it more, maybe. Yeah. So these are different processes, right? So this is process now. This is process P1. This is process P2, right? Now the processor is going to talk to something called as, this is something called as scheduler, right? The process talks to the scheduler. The schedule based on certain algorithm will pick this process, give it to the processor, and then if it's taking more amount of time, what it will do is it will remove this processor out. It will perform a context switch, right? So the state will be stored. And then the next process that is in line will be given the access to, right? What happened? Where did the screen go? Check. Okay, let me. Yeah, so now we have it. Well, this is not sidecar. This is uh let's add a display capture. Okay, so now as I was saying, so what is going to happen is, so now each process, say if this is process 1, so what we can do is we can divide this process into uh, many threads, right? So based on the language that we used, we divide this into threads, right? Now remember, threads is smallest unit of a process, right? Now we may not be able to divide each process into multiple threads, right? The advantage of multi-threading is your context. If you do context switch in threads, the overhead is less. So overhead is less because this process P1 is going to get the heap stack, right? So if we do context switch here, we need to store all this. So this has more overhead when we make context switch in terms of our process, right? As compared to when we are making context switch in 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 threads, right? So now what is the problem that we were trying to understand is, so now what if there are two processes? Okay, so I have So this is, let's say this is uh, process P1, and then I have one more process, right? So this is P2. So let's say this is P2. So these are two processes. So this is process P1, and then this is process P2, right? Now this is a shared memory resource. So what if these two processes are trying to access the shared resource together, right? So now here is the problem, right? So what problem that arises is, the first thing that comes around is race condition, right? So race condition means these two processes, first reaches uh, uh, whichever reaches the shared resource, accesses it, and then changes the value, right? So there is a racing between P1 and P2 happening. So P1 and P2 race for the resource. So this is basically something called as racing, right? We don't want this to happen. Neither do we want process P1 always to occupy the shared resource, right? If you don't, if it's happening that only process P1 is able to access the shared resource, then we are doing something called as starvation, right? So we are not allowing other processes P2 to come and take the shared resource. Now what if P2 never wanted to access the shared resource itself in the first place itself? So P1 should not compete with P2, right? If P2 does not want to access the shared resource unnecessarily, P1 should not compete with P2. P1 should only compete with those processes who want to access the shared resource. For example, if there is another process, say P3, right? Now what if this P3 wants to so this P3 wants to access the shared resource, right? So P1 should will fight with P3, not with P2. So that is basically nothing called as progress, right? So this is nothing but the race condition or the critical section problem that we encounter, right? So the solution to this is, we establish three rules, right? So whenever any process wants to access a critical condition, we need to follow three major mechanisms, right? The first thing that we think is, we say mutual exclusion, right? Now what does this say? If a process has already is if a process is using the shared resource, no other process should be allowed. No other no other no other process should be allowed to access. So this is the first principle of mutual exclusion, right? The second thing that we say is basically progress, right? So now what does this state? If we have two processes, say suppose we have three processes, P1, okay, let's erase this. So we have say process, uh, we have process P1, P2 and P3, right? Now out of these processes, only P1 and P3 want to access the shared resource, right? If only P1 and P3 want to access the shared resource, then P2 should not raise its hand itself, like should not compete for resources. Because what we want to say is, if a process wants to uh, uh, the competition should occur only between P1 and P3, or the process that wants to access the shared resource, right? The third and the final condition that we have here is, we says bounded weight, right? Now what does bounded weight mean? That if we are having three processes, so this is if you are having three processes, say P1, P2 and P3, and all three want to access the shared resource, right? If at first P1 gets to access the resource, so first Uh, so first P1 accesses the resource. Now, what should ideally happen is, since P1 has already got its turn, the competition should be between P2 and P3 to access the resource. It should not happen that P1 is always occupying the shared resource, right? So hence we say bounded wait, right? Bounded wait means that all the processes that are waiting to enter into the critical section should get easy access, right? So basically what we are trying to achieve should be able to access. So what we are trying to achieve here is, basically we are trying to achieve synchronization between the different processes, right? Now so the way to achieve synchronization is something called as, now for two process, if you are only having a if you are having only two processes, right? So then what we can do, if there are only two processes, then we can use something called as Peterson's solution, right? The Peterson's solution will perfectly divide the resources for two processes. It perfectly works fine for two processes. If you have more than two processes, then we again run into a problem, right? Now, okay, so we already saw, right, all the three conditions. So now how does so what if we have another, so what if we have three processes coming into, so basically this is nothing but a software. So for three processes we have something called as Baker's algorithm, right? Now remember, these are all software solutions, right? Or these are basically programs written to achieve synchronization, right? So that there is no race around, and all the processes get are able to access the shared resource. Now now the next thing that we are going to study here now is basically hardware synchronization. So we say support for hardware synchronization, or we say synchronization, achieving synchronization by hardware. So we are saying hardware synchronization. Now in the section we saw, now we refer to this. We have just described one software-based solution to the critical section problem. And this is the software because the algorithm, and so basically Peterson's are basically algorithms, right? There is no special support from the operating system or specific hardware instructions to ensure mutual exclusion, right? Now, however, as discussed, software-based solutions are not guaranteed to work on modern computer architectures. Now, what we do is, if we provide an hardware-based synchronization. Now, okay, let's see. This is something that we need to. Uh, so the very famous two methods of hardware synchronization is basically something called as, um so the two famous method of hardware synchronization is basically something called as, um so we have compare and swap, then So first thing that we need to understand is if we have Peterson's or then why do we need hardware sync? Now if you have software solutions like wait, well, let's put it this way. If we have uh, uh, so what is the need for uh, so if we already have a Peterson solution, okay, so now uh, so basically we were about hardware synchronization, right? So for hardware synchronization we have two main methods, mutex and semaphore. So let's study more about hardware sync. So now there is a drawback of Peterson's solution, right? So let's first study what's happening there. Because the first drawback of Peterson's solution is we waste time. The first is basically CPU time is getting wasted. Now how is this going to get wasted is, so what Peterson's solution says is, or what Peterson's solution proposes is, suppose we are having two students, right? So this is a student one. No, suppose there are two students. This is student 1 and this is student 2, right? Okay. Now there is only uh, one washroom, so you only have one washroom, right? This is student number, so you can say this is number 1. Now what if both of the students wants to go to the washroom, right? So what logically will happen based on Peterson solutions? First is both student 1 and student 2 will say to the teacher, this is the teacher, right? So they will say to teacher that we need to go to the washroom. So what teacher will do is, teacher will say, okay, student 1, you go to the washroom. Now, but student 2 also wants to access it, right? So it will continuously keep on checking whether the washroom has been emptied or not. Whether the washroom has been emptied or not. Whether the washroom has been emptied or not. So by doing this, what is happening is, 2 is continuously wasting time to check whether the washroom has become empty or not, right? Instead, what we want to do is, the moment 1 goes out, we want 2 to be all notified automatically that now the washroom is empty, you can go and use it. Till that time we want 2 to sleep, so you say you go and sleep. The time washroom is empty, I'm going to do an awake to you, you come and use the washroom. So this is big drawback of Peterson solution, that we are going to waste CPU cycles, right? To check whether the washroom has become empty or not. So further taking on that analogy, like the washroom can be the what do you say, uh, the shared resource, right? Now the solution to this issue is, we something deal with something called as uh, so now we come to something. So basically, first thing that Peterson's solution does is, it is going to waste CPU cycle, right? So we want to minimize this. So our goal is to minimize CPU cycles. So now for this, and Peterson's algorithm is specifically defined for two processes, right? But in the practical world, you won't be having two processes, right? You will be having more than two processes running, right? Because we are in the world, we are dealing concurrency, right? So we have more than two processes running at a time. So hence, Peterson's solution is considered as a very what do you say, very theoretical model. The more practical way of achieving is, basically we achieve synchronization using hardware synchronization, right? Or the best way to achieve synchronization and to avoid critical section is using hardware sync. Now, how is hardware sync achieved? So there are different ways to achieve. First is basically using mutexes. Then we have semaphores. Then we have spin lock. Okay, and so on, right? So using this, uh, we would be going to this we would be moving on from Peterson solutions and moving towards hardware. Is the only reason is because of Peterson solution is a very theoretical model in nature, right? So in modern days, first is we won't be having one CPU, one process running, right? And Peterson's solution will only work if there are exactly two processes. So the first drawback is there. The second drawback is basically cycles, right? The process that is waiting has to keep on checking whether the shared resource, whether its turn has come or not. So again, there is a major wastage of CPU cycle, right? That analogy of the student to keep continuously checking off whether the washroom has become empty or not. So that is a very big issue, right? So hence we wouldn't be dealing with that, right? So hence Peterson solutions is basically although it follows all the three principles of the Coffman solution, right? The Kaufman solution is the basis for to avoid critical solution or to avoid the race around condition, right? So it states it has three rules. It should follow. So any software logic or hardware logic trying to implement synchronization should be able to follow the three basic laws. First is basically mutual exclusion. Second law that we says is basically there should be progress, right? That if a process does not want to access the shared resource, it shouldn't necessarily compete for that resource. The third is bounded wait, right? All processes should wait for a specific amount of time, and there should be and it should not happen that only one process is constantly accessing the shared resource. The accessing of the shared resource should happen in turns, right? That means if one p1 accesses, the next turn p2 should get its chance to access. So that is nothing but called as bounded wait, right? We are avoiding starvation of the process. So I guess that is all for this session. I hope you guys liked it. So in the next, we'll start with hardware synchronization, and we will try to understand more about it. Basically, we'll start to understand about mutexes, spin locks, semaphores, and more. So yeah, so that is all for this session. Hope you guys liked it. I'll see you guys in the next one. Till that time, take care. Bye bye. Hello everybody. Hope you guys are doing well. So continuing on our journey, today we would be so we were with hardware synchronization, right? So we wanted to understand more about hardware synchronization. So we will see a little bit about it. So now, okay, so uh, let's so we said that to achieve hardware synchronization there are different ways, right? So let's say, so one of them would be uh, yeah. So one would be using semaphore. Other one would be using, so other one will be using mutex. Then we also have something called as spin locks, right? So we'll see everything in detail, and we'll try to check how and what is happening. So first, let's see what is a mutex. First, let's understand what is the meaning of mutex. So mutex basically uh, so there is a mutex versus. Okay, first let's understand what mutex are. So both mutexes, semaphores, as I said, are synchronization tools in concurrent programming, but they have different they have different uh, roles, right? So mutex stands for mutual exclusion, right? The full form of mutex is mutual exclusion. Now, what does this do? Basically, it is to so why is deadlock coming here? So why is this coming into? Okay, so before we go ahead, I guess we should know what a deadlock is. So let's understand what is deadlock. So before we go ahead with uh, uh, what do you say, hardware sync, let's first understand what a deadlock is and why it's uh, so first let's see what a deadlock is. Okay, so this is basically two words together. Suppose there is a person A. So I have a so this is say person A. Now say this is so this is person A. A person A holds a pen and needs a notebook to write. The person B holds the notebook but needs the pen. Neither will give up what they have. Oh, so this is basically uh, he has a notebook, right? He has a pen. Similarly, but to write, he needs a book, right? But this book is with the other guy. So this is with the person B, right? The person B has the book. So this is book. So what is going to happen is neither will give up what they have until they get the other. So you want, and he needs a pen, right? It's almost the vice versa. So he needs a book. The book is with him, but he needs a pen. Uh, so there is a lock, right? A tie which has happened. Both need the exact opposite thing. So then for this is nothing. This whenever we enter into such a condition, we enter into a deadlock, right? So now how to solve this? We need the solution. We need a solution, right? So for this, again, Coffman came up with certain solution to resolve this, right? So what did he say is, so he placed in four conditions. He said, let's use four conditions to avoid deadlock. First, he said, basically, we let's use mutual exclusion, right? Now, mutual exclusion states that if there is someone using a resource, only one person at a time can use. So, one person can use one thing at a time. Okay. The second rule that is said is hold and wait. So, if uh, so the second condition is hold and wait. That means if a thread holds one resource while waiting for the another, right? So suppose if this is waiting for notebook, right? So he cannot, and suppose he's waiting for pen. So he cannot give up the notebook that is needed by other. He needs to wait until the resource is available. Okay, no preemption. So preemption is basically forcefully taking out. We can't force. Uh, we can't force anything to happen. So basically, he's saying that we can't force. Next condition that is basically circular wait. Circular wait is basically like a circular queue, right? So all threads are put into the queue so that what does this do is this ensures so there is this is like a circular array, right? So you have threads waiting in so that um, Let's this is a circular queue, right? So basically, what happens is this is a circle of execution, right? That if you are having three things, so you suppose one goes out, then the next time second will come in, and then the third will come in, making sure that all of the things are getting the resource, right? So this is basically deadlock, right? So deadlock causes basically cyclic waiting on locked resources. Now, okay, now let's come back to our mutex. So let's see first deadlock versus. But our main goal is to solve critical section, right? So we don't have anything for more than one process, right? So our main goal is basically to solve critical condition, not to create or deal with deadlock, right? So when solving critical section problem, we come into a region where we say we are in deadlock. So let's say about mutex. This is a little bit confusing. So Peterson's solution. So Peterson's solution is basically a theoretical thing, right? Okay, so let's see what all problems can we have when we have multiple process, right? Okay. Okay, so let's break this down. Now, Peterson's solution is more like a theoretical. Basically, first we studied is critical section, right? So this is the main topic that we are trying to study. To achieve this, we said that we need to follow three rules, right? We need mutual exclusion, we need something called as progress, and then third, we need something called as bounded wait, right? So the first scenario that we study is when we only have two processes. So when we only have two processes, so for two processes, we perfectly have a solution, and that solution is nothing but Peterson's solution, right? So this is the perfect way, right, for two processes. For two processes, there is not an issue, right? But what is in reality is going to happen is, so in reality we don't have exactly two processes running. Instead, we'll be having more processes, right? So when we have more processes, or when we are having multiple processes that are trying to access the critical section, then now what is going to happen is, okay, now when we have more than two processes, what all possible things can happen? So the first thing that can happen is the race around. So race around is again the first one wins, or the faster process wins. Basically, two or more process access shared data at the same time, and the final results depends upon the timing, right, on which what is executed. So I have this shared resource. Now, yeah, I have this shared resource, right? Now this is accessed by both P1 and P2, right? So both are writing. Suppose this is a counter. Say I have a counter. So initial value is 1. Now, uh, so both processes are just incrementing the value by 1. So what is going to happen is, now without so suppose uh, uh, and then after incrementing we are going to store the value back, right? Suppose both read the value, okay, increment it, and then write back the result. Okay, so ideally what should happen is, first P1 should for so ideally this should become +1, right? So when we add 1 to it, the counter value will increment and it will become 2. Okay, that's okay. Now ideally what should happen is, when P2 comes and checks, P2 should increment this and then it should make this as 3, right? But then what is going to happen is, now since both P1 and P2 have accessed at the same time, right? So both have 1 inside of them. And then so it should be like, so ideally the logical region should be 3, right? But what is going to happen is, since P1 is faster, it is going to increment and write the answer as 2, right? So instead of getting 3, we got P2. We got 2, right? Because there was no proper like both were accessing and reading at the same time, right? So instead of we waiting for 1 to complete, and um uh then the next one should come, uh what is happening is, uh, uh, both of them are accessing at the same time, right? So that is a big thing, right? So basically racing is the one that uh, executes first, writes, or wins, you can say. The second thing that can happen is, again, when we are into critical, right? both want to write simultaneously. Multiple processes have entered the common resource. There is no coordination, right? So then here we will lead to inconsistencies, right? This is going to get inconsistent data. The third is deadlock. So deadlock is both processes are waiting for each other and none can proceed. Basically, for example, there is a process A that is occupying or that has a resource 1, and B and waits for resource 2. Now B has this resource 2 and it is waiting for 1. So again we are locked out, right? This is a circular thing. Like uh, there is no breaking, right? Starvation is when a process has to wait indefinitely and for the CPU to become indefinitely. So what we do is we do preemption, right? So what if there is a high priority thing? It will starve the lower priority things, right? We don't want that to happen. And so basically, there is a very minute difference between critical section and race around. Yeah, so basically, uh, the trap that we fall in basically in critical section is race around, right? So race around is the race condition is the bug that happens. When we fail to protect the critical section, right? What if so to avoid race around we need to have critical section being proposed, or we need to protect it properly, right? If there is no protection, then the faster executing thing will come and execute, and then we will get the inconsistent data, right? So race around and critical section is closely related to each other, you can say. um to avoid race around is basically racing. So basically to avoid two process based on their time, we need to work on this critical section. So critical section is basically something that is being shared, right? So we need to be very careful, or we need to protect this common resource being shared. So you can think of that analogy as well, the ATM analogy, right? So suppose if there are two people who are trying to access your account, and one has a very fast system, so there are two persons who want to access, right? So suppose you are having say 1,000 rupees in your account, and person P1 wants to withdraw 1,000, and person P2 also wants to withdraw some amount that is greater than 1,000, right? So what is going to happen is, if I'm not protecting this, if there is no protection that only one transaction can happen at a time, what if P2 comes and takes? Oh, also, what if P2 wins, even though there is no enough money because P2 is on a computer which has a very or is a very fast process, does not have much overhead. The CPU schedules it very fastly and it takes out. And there is no money left for 1000, right? Then I would go in minus. I would go in depth, right? I am in negative balance. And at the same time, even this guy is also trying to do. So this guy should be notified that you don't have enough, right? And you won't be able to access. What if 1000 comes and takes it? Now you have zero. So this also is, this guy is not knowing that there is zero, but he's still trying to access the same resource. So that is an issue, right? The other thing that we may go in when we have multiple processes is deadlock. So deadlock is like it's a lock. So dead and lock. So A wants to resource A wants a resource, or A is having a resource one but wants a resource two. B wants a resource two but has resource, so it's exactly opposite, right? So B has resource two but wants one, right? So your one, so there is a lock, right? Who will get what? So we are in that locked zone. Okay, so the practical, in practical we will be having multiple processes, right? So that is when we land up into that conditions. So then is when we go something to mutexes, semaphore and atomic operations to achieve mutual exclusion and other principles. So now let's see what is mutex. So mutex is, now this is something cool. Oh, so is it like, is it something like this? What is happening? Ah, I see what's happening here now. I guess these are working together to solve the issue. Hmm. But also, when we have multiple processes, we are running into that deadlock issue, right? That is also one thing that needs to be taken into consideration. So we need to have an approach that not only solves the deadlock, it also uh, it also follows the three remaining things, that something like hold and wait, no preemption, that should happen. This is a small caveat about deadlock. Oh, so when we have multiple processes, critical section is one of the problem. He's trying to say. But then we have when we have multiple resources, deadlock is also one big issue that can occur. Also, when we are sharing resources in two resources, I see what he's trying to say. We can have deadlock, critical solution, problem. But there are different types of it. So critical section is more related to race around. So for critical section, Coffman has three rules, and for deadlock we have four rules. Oh, so how does uh, mutex solve both issues? So we don't use mutex alone. It does not automatically prevent deadlock, right? We need some other mechanism. So how what? So how is deadlock solved? Then what does semaphore do then? What's a semaphore? Semaphore is what does it mean? So if mutex already solves critical section, why do we need semaphore? And how to avoid? So there are other mechanisms that we can do. There is a banker's algorithm, something. Oh, I see. So uh, mutex and semaphore will solve only one of the problems. of which is critical section. Oh, these are basically one core problem. Ah, so it's this way. So then, uh, so in process synchronization, when you have only two processes, why don't you talk about deadlock there? Why was that not taken into consideration though? Oh, it's specifically designed. Oh, there is progress, right? And there is bounded weight as well. Ah, so both process can't be stuck, right? Because whenever we change that flag, we give it to the other. Oh, this is. So what he is trying to say is. So, so there are two different things. Is what he's trying to say here, I guess. Now I understood what he's trying to say. So the Peterson's algorithms is specifically designed to avoid deadlock. It's naturally made so that the deadlock never occurs there. Oh, that's nice. Okay. So both processes can't be stuck forever. Mm-hmm. I see now what he's trying to say. So what he's trying to say is basically, uh, okay, yeah, now it's working. So process synchronization has two main things, right? So first is basically, for two process, and then second is for multiple process, right? So you have multiple process. So when you have only two process, the only problem that you run into is critical section, that racing around. It's one and it's they are intertwined. But when you have multiple process, not only you have a race around, but also now suddenly, because you have two processes, you will run into an issue called as deadlock. So for two specific processes, there is a solution called as speed resistance. This is for exactly two processes. Now for multiple processes, we use for race around we have two things. You have a mutex and semaphore. Both are working on this critical section thing. For deadlock avoidance, we have something called as test lock or something like. So this is basically is what is going to resolve the solution over there. or to avoid deadlock. Okay, so yeah, I guess that is all for this session. I hope you guys liked it. I'll see you. So whenever you are solving critical section, you need to. So when you one more thing, one more thing. What happened to the Zoom? Yeah, whenever you are going for or whenever you are trying to solve the what do you say race around condition or critical section, there are three things that you will be looking at specifically. First is the three Coffman conditions for critical condition, and when you're solving deadlock, to avoid this, so Coffman is made for deadlock conditions, so those need to be satisfied. Like those need to be avoided if you don't need any deadlock happening. Okay, so I guess yeah, this is all for this session. I hope you guys liked it, and I'll see you guys in the next one. Till that time, take care. Bye bye.